Today on Capechi's Corner, we're going to look at graphing exponential functions. So what is an exponential function? Well, it's a function that has this form where we have a base raised to an exponent. Now, a couple things. We know a can't be 0, b can't be equal to 1, and b has to be greater than 0. For instance, x is equal to 5 to the x power. Now, we're going to look at exponential growth and exponential decay today. The first one is exponential growth, and it is exactly as it sounds. It's a quantity that increases exponentially very quickly over time. So, what happens is we know that this power has to be greater than 1 when it's an exponential growth. An example is the number of cases of COVID-19 in the United States in the year 2020. Now, this was not, unfortunately, just a steady climb where there was one day there was 10, and the next day there was 20, and the next day there were 30. The number of cases grew exponentially because they grew very quickly, very high, very quickly. So this is what a parent function of an exponential growth looks like. So again, it gets very, very high very quickly. So as x increases, y increases. Now, we can also talk about the domain and range, which we do a lot in math. The domain, meaning my x values, I can go from left to right, and I do have arrows on the end. So there's nothing that I cannot have. So we have all real numbers. Now, when we're looking at our range values, our y values, we do have a limit. So what's going to happen is we're getting very, very close to 0, but we're not touching it or crossing it. So in that case, we can say all positive real numbers. We're going to use the notation that says f of x such that f of x is greater than 0. Now, we do have an asymptote with exponential functions, and that is when a line that it graphs on the function approaches, but it doesn't get really close. In this case, because it's at 0, our asymptote is found at the x-axis. Now, we also have some transformations which we've used before. There's kind of our initial setup for our formula, and we're talking about horizontal and vertical translations. The vertical translation is going to be a little bit easier to see. It's going to go up or down. The horizontal, the value for h is going to go left or right. All right, now let's talk about some exponential decay. It's again sounds like what it is. It's an exponential decay. A quantity decreases exponentially over time. Very quickly, it decreases. Now, with that, what we have is we have to make sure that we're paying attention to what our values are. So our b value here is going to be between 0 and 1. Now, our value, an example we have is a value of a computer. You buy a computer today, it's not going to be worth a lot of money in 3 years or 5 years or even 10 years because of the fact that technology improves so rapidly. And that tends to be true for a lot of items, whether it's some type of watch, whether it's a computer or a phone or a laptop or an iPad, so anything like that loses its value very quickly. Now, again, we have all real numbers, we have positive reals, and we'll do a lot of different things when we're talking about this with our domain and range. All right, so let's look at some graphs. So I have y is equal to 3x, and I set up the table just to make things a little bit quicker. So again, we do have an exponential growth, and so our domain is we can go anywhere on our x-axis. So we have all real numbers. That's going to be our domain. And if you look at our range, and you can get that from either our table or our graph, I can see that it's not going to touch 0. Same thing here. I'm getting really, really close to 0, but I'm not going to touch it. So my range is y such that y is greater than 0. All right, let's take a look at our next one. We have y is equal to 2 to the power of x plus 1. And what I did is I substituted x again everywhere I saw it, and I created a table. So now again, you can see an exponential growth there. So my domain, again, I have arrows on the end, so I have no limitations, all real numbers. Now you can see from my table, I'm getting very, very close to 1, but I'm not touching 1, and that is really because of that shift right there. So in this case, y such that y is greater than 1. Can't be equal to 1. It's not going to touch 1, but it's going to get really, really close. All right, and number 3, we have a lot going on here, so I definitely wanna use my calculator. So I pick values of negative and for my x, and what happens is when I started picking my normal type values, -2, -1, 0, I realized I was not getting a lot of movement. So I said, "Well, let's jump and see what's going on." So I picked -5 and -10, and the graph still did not shift a lot, but again, it kinda gave me a little bit better of an idea of what's going on. So again, in this case, my domain, I do not have any limits, so it's all real numbers. And my range, I can see I'm going to get very, very close to y, but I am not going to touch y. So since I'm not going to touch y, I'm going to y such that y is greater than 1. All right, let's take a look at our last example today. And this is really where we use exponential decay and growth. You hear a lot of it on the news. Here's a real world example. Okay, so we have an exponential growth. We have 1 plus r is inside and 1 minus r when it's a decay. So what do those values stand for? Well, what we're starting with that a of t, that's the amount after any t time period, anything we have for the time period. R stands for rate, t stands for time, and a is the initial amount. So we'll know if something is going to get larger or smaller based on what is in those parentheses. Okay, so let's take a look. In 2006, there were 1,020,000,000 people worldwide using the internet. At that time, the number of users was growing by 19.5% annually. Draw a graph showing how the number of users would grow from 2006 to 2016 if that rate continued. So here is our equation. Right? We have what we're starting with, right? That's our A value. And then we know we're growing. So we know we're going to add there. And then there's our 19.5%. Okay. And then that T is we're going to change as we fill in the graph. Okay. So what I just did is I just used my calculator and then I kind of plugged in values and I plotted the points. So what we have here is we started at now again we have our users on the left hand side here. That's our y-axis in billions. And on our x-axis, we have our time, which is what we usually have on the x-axis. So again, we started with in 2006. We started with 1.2. We have 1,020,000,000. So we started right about here, and then I substituted some values in. Now it's just asking for this particular range. So I am going to see a little bit, of an exponential growth here. I'm not going to put an arrow on the end because they're not asking for a continuous function. They're just asking between that time period. So there you can see that the number of users is definitely jumping exponentially within that time frame. Now, one thing you just want to remember with anything when you're talking about specific years, that when I'm substituting for T, for instance, I'm not substituting 2010. I'm only substituting 4 in for T because my starting point was 2006. So that is 4 years later. So that's going to be my time frame. Okay. Thanks for stopping by today. Have a great day.